everyone. Today is going to be your first lecture of the second week for this semester. Crystallography Part 2. These are all the topics that we're going to cover this week. 7 crystal systems with 14 Bravais lattices, theoretical density, and I'm going to talk more of packing factor, especially for hexagonal close packed. Real and reciprocal lattices. Lattice directions and planes mirror indices, interplanar spacing. By the way, I recommend you to read more from Chapter 2 from this book, Elements of X-ray Diffraction, written by B.D. Quality. Let's take a look at this picture. So this picture is gonna represent the lengths A, B, and C. So this one we call lattice parameters. Okay, again, A, B, and C. And also we have interaxial angle. So it's the angle between each length. So the angle between A and B, we call it gamma. B and C, we call it alpha. And from A and C, we call it beta. The way I remember is like this. So I show you how we can memorize this. So we have, remember we have lattice parameters A, B, and C, and then you write down interaxial angles, alpha, beta, gamma, right? Normally you say like this, alpha, beta, gamma. So the angle between A and B, we call it gamma. The angle between B and C, we call it alpha, right? B and C. And the angle between A and C, we call it beta. So this alpha, and this is gamma. Okay, so this is how I normally use this way to memorize. But you may have your own way to memorize, okay? Now let's take a look. 7 crystal systems. Cubic, tetragonal, orthorhombic, trigonal, or rhombohedral, hexagonal, monoclinic, triclinic. The way I remember, okay, let's I take a look at this first, okay? So the top, right? The top, take a look at the cubic first. The cubic, all the lengths are the same. A is the same as B, is the same as C, and all the angles between them are the same, and it's 90 degrees for each. Tetragonal, imagine that you stretch in vertical direction, right? So C in this picture is stretching. or you can think of like reducing, but whatever. A is the same as B now, right? But it's different than C. And in this picture, C is larger than A. And A is the same as B. But all the angles between them are still the same, 90 degrees. Let's move on orthorhombic. You stretch this way, trigonal, and then now you stretch another way to the horizontal direction, or you could shrink if you want. So A is no longer the same as B, right? Because you're stretching in the horizontal direction, and it's not the same as C, and all the angles, right, still the same. So this 90 degrees, they are perpendicular to each other. Okay, so now let's write down 7, right? 7 crystal systems. How we can remember all the names? So this is C, T, cubic, tetragonal, O, T, trigonal, and H and M. You know this brand, right? H, but how now we have H, M, T. H stands for hexagonal, and M stands for monoclinic, and T stands for triclinic. Okay. We already know this one, right? So let's do this. So this one, and this one is repeating here. Only all the lengths, right? So it's like you copy this, copy this, copy this here and here and here. Okay. Now let's take a look one by one. So for trigonal, A is the same as B, is the same as C. So this is AAA, right? But all these angles are the same as well, right? But not 90 degrees. So it's opposite here. So this is 90 degrees. Here's not 90 degrees. Move to hexagonal. Hexagonal, right? So this is C stretching. So we have learned it from last slide. Alpha is the same as beta and is 90 degrees. But gamma here, gamma is 120 degrees. Monoclinic, all the lengths are different. Angle alpha and gamma is 90 degrees. Beta is not 90 degrees, as you can see here. And most of the time it's like larger than 90 degrees, right? So it's tilted that way. For triclinic, it's unsymmetry, right? Non-symmetry, all the lengths are different. And all the angles between each length are different as well, and it's not 90 degrees. Okay, so this is how we can memorize this 7 crystal system. Now we have 14 Bravais lattices with its own group of system. So we already have learned cubic, right? So this cubic, we have at the corner, 8 corners, we have 1 atom sitting on each corner. And BCC, right? In addition, we have 1 sitting at the center, and FCC, so we have 6 atoms, 1 of each sitting on 6 faces. So we have familiar with this system. So we have P, I, and F, okay? Tetragonal, we have 2, orthorhombic, we have 4, and monoclinic, we have 2. And if you count them all, it's 14 Bravais lattices. Unless I zoom up the first 3 top, again, here is much more clear. Cubic, tetragonal, orthorhombic. So P, when we have simple cubic, right, only at the corner, only lattice points are only at corners, P. When the primitive lattice points are at both corners and body centers, the cell is labeled I. So here we have I. 4-face center cubic, right? So in the case of primitive lattice points are at both corners and face centers, the cell is labeled F. So this is F. So we have 3, right, for cubic. For tetragonal, we have 2, because one is stretching along Z-axis or along C length. And when we add 1 at the center, so this is BCT instead of C cubic. Here we have the tetragonal. At the center, we have labeled as I. For orthorhombic, we have the same P, I, F, and change from cubic here, right, to orthorhombic, 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 P, I, F. And we have one more here. So this is BCO, right? Base center orthorhombic. So we have 1 at the top surface sitting in the middle of the top surface, and another one sitting in the middle of the base. So this label C. Trigonal, we have only 1. Hexagonal, 1. Monoclinic, we have 2. Simple monoclinic, labeled as P, only at the corners. And here, in addition, we have 1 sitting at the middle of the top surface, another one sitting at the middle of the base. So this label as C. So this one we have 2. So when we count them all, we have 14 Bravais lattices. These are some examples of some materials, and on the right side are the crystal structures. Let's move to theoretical density. Last week, we have learned how to compute packing factor. And theoretical density is similar idea, but maybe a little more things to calculate. First, let's review, give you a quick review. So number of mole, the definition is gram per molecular weight, right? Amount in grams and molecular weight equals to the ratio of number of atoms divided by Avogadro's number, N sub A. So this is Avogadro number 6.8 0.023 times 10 to the 23 atoms per mole. And you know this meaning. So this is the definition of density, right? It's just mass per volume. So I put gram per volume. Then from this equation, I can write down gram is N over Na multiplied by molecular weight. Okay, MW here. So this gonna be the formula that we will try to use to calculate the theoretical density. Okay, let's take a look at an example. Determine the theoretical density for iron. Okay, so first, if you have a textbook, especially for Kittel, right, or for Ashcroft, you can open up. They have like tables and say, okay, iron. What is the crystal structure for iron? So first you have to know crystal structure for iron. BCC. Okay, so we have BCC and you already have done it. So we have 2 atoms per unit cell, right? 1,8 times 8 plus 1 in the middle. So 2 atoms per unit cell. Atomic weight, 55.85 grams per mole. Another one that we have to know is atomic radius. So I wrote this for you, right? 0.124 nanometer. Okay, so for BCC, go back and review by yourself. First, you have to know the relationship between A, the lattice parameter, and R, the radius of atom. Okay, so once you know that, right, and you know that the unit cell, the volume of the unit cell is A cube. So plug all this in this formula. Okay, and you will get this number. Can you do this one by yourself? Okay, you can pause this slide and try to convince yourself this is the number that you get. Okay, and then you open up the book. Okay, and then you, wow, okay, let's see. The number written in the textbook, 7.87 gram per centimeter cube. Oh, it's close, very close. So even though like here, we assume that the atom is solid sphere, but actually it's not really solid sphere, right? I mean, solid sphere mean what? I mean, you cannot compress, something like that. But in real, I mean, you know that all the electrons just cloud, right? Probability of finding electrons like just like clouds, you know, it's not like a real solid that you cannot compress it. Okay, but I mean the numbers that these two have are close enough. I mean, not bad, right? Okay, let's see another example for copper. Okay, so can you do this by yourself? First, you have to know what is the crystal structure for copper, right? So once you know that, you will know that how many atoms, okay, per unit cell, right? Okay, and then plug all these that are given, especially go and prove by yourself the relationship between the lattice parameter and the radius of atom is like this, and then plug all the number. Okay. Next, packing factor. Last week, we have done packing factor for simple cases. Simple cubic, body center cubic and face center cubic. And here is a little more complicated for hexagonal close packed or HCP. Let's I show you. Okay, let's see. Here I have model. You can see here. I'm gonna rotate. Okay, do you see? And the base is just like this. We have done it last week, right? I recommend you to draw it using poise on the paper. So this is the base. And if you draw a straight line from here to here, here to here, here to here, here to here, like that, right? So you will get something like this shape. 6 faces. 1, 2, 3, 4, 5, 6. Okay. So just like that, right? Like this. You can use this. Like that. Like this. Like that. This and this and this. Okay. So this is the base, the same as the top. Okay, so this is HCP, hexagonal close packed. Okay. The one in the middle here. Okay, the one in the middle. So this is, remember, it's A, B, A, B, right? A, B, A, B. I will remind you that it's different than this one. So this is A, B, C, A, B, C, and go so on. Okay, so if you look at this, you will see this shape is like triangle, right? And then another one, this level is another triangle and cross each other. Okay, so this is ABC, ABC, but is FCC. Okay, it's not HCP. HCP has to be like this. Okay, like this. Okay, great. So what is the ideal for C over A? What is A? This is the A. And C, from here to here. Okay, so this is C. Half of it is C over 2. Okay, half of it is C over 2. So the way to do the packing factor for HCP is, first you have to get the relationship between C and A to see what number do you get. Okay, so I give you an example of the drawing here. So this, remember when I show you the base and you draw it like this, right? So notice that we have one area, second and third, fourth, fifth, and sixth. So 6 areas in total. Okay, let's focus 1 here. This is this. And this is C over 2. C over 2 is this. From the base to the middle. Okay, because of this is C. Okay. So right in the middle, let's call it X star. Okay, star here. Draw a line from A to A prime and O to O prime. Since you know this is similar triangle, right? That means all these lengths are the same. So that means like each angle is 60 degree, because 60 degree multiplied by 3 is 180 degree. So half of this is 30. So this right triangle. And you use the Pythagorean theorem, right? That for right triangle, you have the length of the legs of the triangle, sum of its square, right? I mean, this length square plus this length square equals to the hypotenuse square. Okay, you can review this by yourself again, Pythagorean theorem. And you have to know all these cosine angle, especially here cosine 30 degree is square root of 3/2. So it's A prime, this length, right, divided by AB, this is AB, hypotenuse length here, okay? And AB, okay, AB here, right here, this is AB, is 2 times the radius of the atom. So we use as A, okay? A is 2R. And solved out for that, you said A prime. So this A prime is A square root of 3 divided by 2, and it's the same as O prime. So A 2x is 2/3 of A prime. And you know A prime from here, right? This is 2/3, it's just constant. So we solved for AX. And you have C/2, which is this part, right? Go on top. And then if you draw from here, A to C, this is C/2, okay? So now imagine this is like really, really packed, okay? Really, really packed. So this one will be big like this, and this one will be big like this, okay? Here you have 2A, right? From A to C. And then use the Pythagorean theorem again. Okay, this is just the math. Can you do this by yourself? And then you figure out that C/A is 1.633. Okay. And then now, for packing factor, remember, we have to know how many atoms, right? How many atoms in the unit cell. Go back again. 3 inside, we have 3 for sure, right? And 1 top, second one on the bottom, and this one cut half. Okay, so when it cut half, so we have 1/2 multiplied by 2. So we have 1, 2, 3, and 4. And how about all these and all these? Can you think about that? You can take a look at this. Let I give you a hint here. This angle, right, is what? 120 degree. Because this is 60, right? So this 60 plus 60 is 120. And you know that in the circle, right, all this angle is what? 360 degree. So this 1/3, right? 1/3 of this. And you know that on the base and on the top, the atom is cut half, right? Like that. So from the base, we have 1, 2, 3, 4, 5, 6. And at the top, we have 1, 2, 3, 4, 5, 6. So 6 plus 6 is 12. So we have 1, 6 multiplied by 12. So this is 2. Okay. So remember, we have in the middle, we have 2, right? Top, middle, and bottom, middle face, right? At the bottom or base. So this is what? 1/2 plus 1/2. Oh, sorry, in the middle we have 3. So I erase this. So 1/2 plus 1/2, we have 1. And another 2. 3 plus 1 plus 2. Total is 6. So another 2 is from this, okay? So this will be 6 here, okay? And 4 divided by 3 pi r square, right? So this is the volume of one solid atom divided by the volume of the unit cell. Okay, so now let's go to the volume of the unit cell. So it's just the area of the base, right, multiplied by the height. So the area of the base is 1/2 multiplied by AB right? 1/2 multiplied by AB and multiplied by what? The height, O prime, right? Base and height. But you have 6 area. So I circle with different color. 1 area, 2nd, 3rd, 4th, 5th, 6th, So we have total 6, right? 6 times the area of this one. So this is the area of this triangle right here. Okay. And then plug all this in, right? The volume of the hexagonal is the area, right, of the base multiplied by height, and height is just C. Okay. And try again by yourself this one, and maybe like do it one more time. I will have this for you as the homework in addition to the calculation for packing factor for diamond structure. So let's I show you the model. I have it here for diamond structure. Okay, so this is it. Do you see? So if you see this, right? I rotate around, okay? For diamond structure, all the colors here, right? All the colors, the blue and the white color is what? Is carbon, okay? It's carbon. But for zinc blend, right? For zinc blend, the white one, do you see here? The white one, maybe I can with different angle. The white one that inside of the cell, for example, like zinc sulfide, zinc atoms will be all the blues coordinations. And the white would be zinc. Oh, sorry, it will be sulfur, right? Zinc sulfide. Or cadmium sulfide, all the cadmium atoms are the blue. And the white would be sulfur. Okay. You see this? Yeah, okay. Okay, let's move on. Rhenium has an HCP crystal structure with an atomic radius of 0.137 nanometer, and C per A ratio is 1.615. Calculate the volume of the unit cell for rhenium. So we know the relationship, right, of the volume of the HCP. So you just plug all this number here and get the number here. And if you take a look at this is like hexagonal symbol here. I think that's gonna be the end of this video. And if I can get more models for you next time, I will show it to you again, so you feel like maybe have better vision, you know. And I'll see you again next video. Thank you for listening. Bye.